Hey, it's Cam with Madrona Labs. Welcome back. Have you ever wanted to embed pictures into your music? Or maybe you want to listen to a visual texture? Well, today I'm going to show you a doorway to some insane spectral sound design using a tool that converts images into partial sets for Sumu, our additive spectral synthesizer. So stick around and I'll explain it all. Okay, so for the new folks out there, welcome by the way. Sumu is built on the concept of resynthesizing sounds using what we call partials. These are like detailed sonic fingerprints we create by analyzing audio. But what I'm showing you today is an alternative method for creating partial sets that begins with a picture rather than a sound. So instead of reconstructing a sound, we are playing with patterns of light and shadow and turning that into something audible. This isn't an official integrated feature, by the way. It's just an experimental thing I did for fun. You can read more about that process on our website under Team Notes. With that out of the way, though, let's go step by step, and I'll show you some patch examples after that. Feel free to skip ahead using the chapter markers. Otherwise, you will need Sumu. The full version or the trial version will work if you want to test it out. The img2utu Python script, link in the description. Python 3 and the Pillow library installed on your machine. And of course, an image. Once you have everything you need, create a new folder inside your partials directory and place the script inside. Then open the command line and navigate to its location. Now we can run the script with this basic command. You can use a single image or process a batch by pathing to a folder. Hit enter and your terminal should look like this, and a new utu file will have appeared. Now open Sumu and re-import your entire partials directory. We want to do this every time we generate a new partial set and make sure we do the entire directory so we don't mess up the hierarchy of the folders. When that's done, you should see your new partial set on the list. Select it, and now we can hear the patterns of light and shadow in our image. I've created a basic patch called image scan as a starting point. There are a bunch of options we can adjust to control how the picture is interpreted, and that's done with these little flags you add to your command. The full list of them is available in the README. Let's go over a few of them together. Starting with the print options option. Adding this flag will extend the file name to include any options that you added that differ from the defaults, not including itself though. This is super helpful when testing many iterations, so I started with that one because I generally add it to everything. Next, let's look at resize mode. The partials window has a 10:3 aspect ratio, so the resize mode tells the script how to crop or fit your image into this frame. The default resize mode is fit width, which maximizes the horizontal space and trims excess off the bottom. As you can see though, you might not want that, so we have 5 other resize modes. Feel free to pause here and take a closer look at each one. Another way we can adjust the appearance of our image is by increasing the horizontal resolution. The vertical resolution is maxed out at 64 because that's Sumu's limit for the number of active partials per voice, but the horizontal resolution, on the other hand, is created with steps in time, which we can increase with this density option. Density 1 is the default, and that gives us 213 steps in time, creating the appearance of square pixels. The number you pass with density is a multiplier of 213, so a density of 2 will create 426 steps in time. Increasing the density can help enhance the details, but also might make your picture look dark. You can offset this with gamma, which applies a curve to brighten things back up. Now let's move on to what we can do to change how the image sounds. Since the vertical dimension is frequency, the way this is mapped has the biggest impact on what the results sound like. And as I mentioned before, the vertical resolution is capped at 64, so the script has that many pitches it can select. By default, it calculates 64 logarithmically spaced frequencies between the default range of 20 to 20,000 hertz. These options here let you change that range. While these tones are evenly spaced visually, they tend to sound atonal or clangy, so we also threw in the option to quantize or snap these pitches into tune. And that option changes the type of sounds you can get dramatically. Here is the list of available scales. They're simply note masks of ones and zeros that toggle pitches on or off within your tuning system. So keep in mind, the names they have here are only accurate with 12-tone tunings, such as the default 12-tone equal temperament. And you might not want to mess with different tunings at all, but if you do, you can pass the tuning option and point it to a Scala file to import any tuning under the sun. Going back to the default tuning system though, what if you wanted a different subset of notes than what the scale list provides? Well, you can simply type a string of ones and zeros after the scale flag and make your own. One cool thing about this is that your custom note mask will repeat to cover the entire frequency range, regardless of where octaves are. So by typing a mask that is shorter or longer than the number of divisions per octave, you can create strange aperiodic note clusters. But I think we dove deep enough into the configuration side of things for now. Let's get into some experiments in creating picture-based patches. I have this little collection of pattern books from the days before there were stock image websites. So if you can imagine, graphic designers back then would buy books like this and photocopy or cut them up. Each one is filled with these amazing patterns, all categorized into themes, and I think these could make some interesting partials. So I'm going to take a break from talking for a little bit and let you listen to some of the patches I made with these patterns. Yeah, so those patterns worked great, and I put a bunch of them in the Madrona Labs goodies folder so you can try them yourself. My main takeaway from this first round of experiments is that negative space and variety are both good things. Patterns that were consistently dense sounded fairly homogeneous. By far my favorites were these arrangements of letters and shapes, which work great as spectral visual scores. I've also included this ambient patch you're listening to now in the goodies folder. I could listen to it for hours. But next up, let's try importing some photos. Plants and animals have interesting silhouettes. And don't you think a pagoda on its side looks a bit like a waveform? And I'd recommend using Pulse's probability controls to scan through specific parts of the image. Try setting the probability below 1 to get a different selection of pulses each time. Definitely try mapping this to hardware control. Anyway, I also thought these metal balls sounded cool. And this leaf sounds crazy. Returning viewers probably know already that I love the high scale control. Yeah, I might just not finish the video and stay here. Let's try switching everything up. We're going to get the pitch from a MIDI controller and instead patch our partials to the mod side instead of the carrier. Now, instead of generating our tones directly with the spectral data, we're adding harmonics by using it as a strange FM source. Okay, I have one more experiment that I just have to try. So normally, we analyze audio with img2utu to make partial sets, and the results in the partial window look a bit like a spectrogram. So what if instead, we took an image file of a spectrogram and imported it with img2utu? Let's try it out. Here's the source. Here's img2utu's version. And now imported as an image. So the frequency content of the original sound has been steamrolled by the image script's even spacing. This leaves behind a ghostly spectral imprint of what the sound generally is. If your goal is to resynthesize a sound accurately, definitely use img2utu. But there is something cool about this roundabout trip from sound to image back into sound again. I tried this with a variety of samples. More tonal things didn't translate so well, but drum loops definitely did. Before I sign off, let's listen to some of those. Alright, well I hope you enjoyed that excursion with transforming images into sound. Check out the link in the description for the script, as well as patches and partial sets I used, and do let us know in the comments about your own experiments. Check out our channel for more Sumu videos, and subscribe so you don't miss new ones. That's all I have for today. See you later. Bye.